So we are happy to have today Erika Bertolini. She's our new junior postdoc. She just graduated. She's going to graduate very soon at the Genoa University, and she's going to talk about Maxwell's theory on fractons today. Okay.
Yeah, thank you. So today I'm going to speak about two of my most recent papers concerning the development of a Maxwell-like theory of fractals. I will show you what about Maxwell theory, but first, what about fractals? Not too much. So you may have already listened a bit about fractals or maybe catch the names, but I want to make it a bit more clear exactly what are fractals. But they're quite recent quasiparticles. They were born. First paper is of 2005, but we can see that the big rise in interest could be seen around 2017 from the works of Maxwell-like. And what's very peculiar of these quasiparticles is that they can be found in quite a large areas of physics. Indeed, looking just at the titles of this papers of Fractons, well, you see the topics. We're talking about big liquids, magnetism, gravity, elasticity, circuits, so quite a lot of topics, and this is also evident from these graphics. Indeed, fractons are both in mathematical physics, condensed matter, quantum field theory, and information theory. Well, they started in information theory. But what's the common feature of these quasiparticles? There should be something that links all these areas, and yeah, indeed, fractals are defining by being quasiparticles with restricted mobility. True fractons are completely immobile objects. They are zero-dimensional particles. While in these models, there are also other kind of quasiparticles that have some kind of still restricted mobility, but less restricted. So they are typically called linears and planons, so you can see by itself the reason for the name. These can move along line, or these on a plane. Here I'm saying it 1D and 2D, meaning spatial dimensions. But physically speaking, I have to build model for fractals. So what does it mean exactly, restricted mobility? Because talking to many people, there are different points of views of what a fracton could be. In a sense, it could be a particle with zero dispersion relation, so with omega being equal to 0. From a quantum field theoretical point of view, one can think also of something that does not propagate. So in a sense, it has trivial propagators. Or it can be a particle with some kind of kinetic constraint on its motion. So there are, in this sense, there are some different languages that can be used to describe fracton quasiparticles. And there are mostly two big areas in which one can find these models: lattice theories and tensor gauge theories, those defined by Bertolini, which are more my area of expertise, but these are very frequent. We've heard something in the last seminar. And concerning lattice theories, well, these fractons can be found in exactly solvable spin models. They were born in the context of building quantum error correcting codes and are gapped in the sense, well, these are massive theories. And they are divided into two classes depending on the particle content. There are type 1 fractal models, which contains both fractons, linears, and planons, and type 2 fractal models that only contains fractals.
Were you referring to the quantum error correcting codes, or are you referring to the Kitaev toric code or something?
Yeah, I mean, there are those models.
In particular, generalizations, X cube is a generalization of the guitar.
Okay, put the quantum error correctly.
Yeah, just from original.
Yeah, the first.
Okay, because they cropped up originally, they believe in the diagonal and the guitar and the Kagome lattice.
Yeah, maybe see. Yeah, I think so. I'm not an expert on this part, but yeah, I think so.
Way back.
Way back, I see.
And
60s or something.
oh, while on the second class of fracton theories, gauge theories, well, these are fractals with described in terms of higher momentum conservation, in the sense that they are characterized by dipole or quadrupole conservations. They are written in terms of rank 2 symmetric gauge fields, where these are special indices. And these are Laplace theories, or massless theories, and they are Maxwell-like models. So, for instance, they have an Hamiltonian which is E squared plus B squared. And I will show you this better in a few more slides. Concerning limited mobility, these fractal models in gauge field theories are comes from a Gauss-like constraints. So, concerning the history and the application of these fractal models, well, they were born in the context of condensed matter and spin glasses. In a way, they were useful to build models for describing materials that slowly reach thermal equilibrium. They were used also in quantum information to build robust memories, and also since they are higher spin models, so written in terms of rank 2 tensor fields concerning the gauge theory, they can be used to describe higher rank spin liquids, for instance. Obviously, since their definition is based on dipole conservation, all physical systems with dipole conservation, dipole symmetry can be related to fractal models. And also, there is an interesting relation called the fracton elasticity duality, which can be used in order to describe topological effects, mostly in 3 space-time dimensions. So, a bit briefly on the lattice models. I'm not an expert, so I'm sorry if there is any in this room, but I think it's interesting to show briefly the history and how these fractals are conceived, and what are these fractals in these models. Well, in this paper, this was the first time that fractals can be seen, even though the name of the fractal quasiparticles came out only in 2016. But this historically is probably the first model which shows a fractal-like behavior, meaning something that is a zero-dimensional.
And with the lattice, with that paper, what dimension do they show this in?
I think it's 4-dimensional.
4.
Yeah, I think so.
Meaning 3 plus 1.
3 plus 1, yes.
Okay.
Yeah. And well, subsequently, the type 2 fractal models, so just the purely fractal particles, were developed by Tal in this paper for the self-correcting quantum memories. And finally, the prototypical model of the type 1 fractals, the X cubed model, was developed in 2015, 2016. And well, what kind of fractals are these? In this model, one has something like operators like this. These are spin-like operators, and one can think of building an object like this, which is called membrane operator, by applying these line objects. So what are they? What's their property? It's a property in the sense they flip the spin, that flips the color of these cubes. And so we can see that in the corner, these blue corner are identified as fractons, in the sense that they cannot move unless they produce another kind of particle. So unless you give some energy for them to produce something like another kind of particle, by applying this red line operator. So this operator flips the color of the cube, so the blue one becomes white, the other three becomes blue. So this one moved on the right in a sense, and these two blue, by sequentially applying these line operators, can move up. So in this sense, we have a fracton that moved by producing a linear. So an object that can only move along one direction. So this is a quick example of a fractal models of a fractal in lattice models. Well, it's necessary to mention also the works of Seiberg and Schau on continual quantum fluidness. They studied continual quantum fluidness of certain lattice models, and by using the definition of fixed global symmetries, so symmetries and continuity equation with higher derivatives. So now I'll step in my more comfort zone, and I go into the gauge field theory solid and the QFT. So what's the constraint on the motion? How can one have fractals in a gauge field theory? How can we have it? Well, the idea comes from Maxwell theory. Well, the Maxwell theory is a Gauss constraint. What is that? That is simply the divergence of the electric vector field, right? In this case, we have an electric field, electric-like tensor field, which is symmetric, and have two indices, and we have a double derivative. This allows for a dipole conservation in this sense that integrating on a volume and multiplied by x, the total dipole moment of the system must be conserved. And thus, we have that single charges, this row, can be identified as fractals in the sense that they cannot move in space unless they break the dipole conservation. On the contrary, dipoles can move freely because they conserve this conservation. Okay, so how to build a fractal model in the context of gauge field theory, a scalar fractal model, for instance. We need a symmetric rank 2 tensor field with spatial indices. There is the need of the Gauss constraint and the symmetry. The transformation of the gauge field is gauge-like symmetry with two derivative and a scalar gauge parameter. The Hamiltonian, as I was mentioning before, is Maxwell-like, so it's a squared plus b squared. And with the electric and magnetic field with this shape. In particular, here we have an A0 field, which is introduced in the models in order to implement the Gauss constraint. So it's a multiplier. It's called A0 because it reminds of the zero component of the Maxwell gauge field. However, in this case, it has no relation with the standard symmetric tensor field. But the Gauss constraint we've seen before, this one, is not the only one. We can also generalize these models and implement something like vector condition. So we have vector charges because this is called the vector charge theory. And what's the point of this? This adds some other particle content to the theory. So we also have the previous constraint because we just have to take the partial derivative of this relation, but we now have also the conservation of this vectorial charge, which we can see as a dipole, and also of this angular momentum, which means that single charges now are constrained to move only along the line. So we have a linear, a one-dimensional particle.
And E is still symmetric, a symmetric tensor.
Yeah, it's always symmetric, yeah.
And do you have any statement about the derivative with respect to I of rho I? The divergence or the...
If we take the divergence of this,
Yes.
we have also the previous constraint.
You're imposing both.
Yeah, I mean, by imposing this, you also have the one before. By saying that this scalar rho is simply the divergence of this Victorian rho. So it's a theory in which you have both a scalar charge which cannot move, so it is a fracton, and also a vectorial charge which can be seen as a dipole, which can move only along the line. So we have two kind of particles.
Here, the ij is around spatial indices.
Yeah.
But E is a function of space-time coordinates, depends on time as well.
It's space. One can also think of adding some other constraints, for instance, tracelessness on the electric field, and this simply further constrain the motion of the previous quasiparticles. So now, if we do this on vector theory, we further constrain the motion of the linear, and this makes it an immobile particle. So we have fractons again. And we can do the same with the scalar charge theory. Now we have the so-called traceless scalar charge theory, and this gives the conservation of the components of the particle moment, meaning that, well, at the beginning we had fractons, and, well, they were immobile, they're still immobile, but now the dipole, which were free, are constrained by the particle conservation. So they are plane. They can only move on the plane which is transverse to that direction.
I'm missing something.
Yeah.
I mean, the time dependence of this, you must be making some assumption about it. Yes. Are you assuming that rho is time independent? And what are you doing?
No, there is no assumption here.
So there's no constraint on the derivative of rho with respect to time.
No, I'd say no. These are not my models. These are the models in the literature. I'm just showing what's in the literature.
The derivative of respect to the time can be related only to also the derivative space of the current.
Of the current, yeah. Yeah, there is a relation there.
In a covariant way, that is the only constraint.
But you are, yes, okay.
Yeah.
Then involving day zero, which is like before shadow time.
Yeah.
Yeah.
Can you ask the Yeah.
There is this continuity equation.
Yeah.
Oh, so you're going to introduce a Jij.
Yeah, this is a dipole current. Yes.
And what is the full field equations? Then I'm happier with full field equations rather than just static field equations.
Yeah, I'll come to that.
Okay.
Yeah. Okay. One last thing, I was talking at the beginning about the interesting fractal elasticity duality, and this is a nice practical example on how to use fractal models, which sometimes we see, but I don't know. These are, but if we find something about fractons, we can also infer something about elasticity theory by using this duality, which tells us that the electric field and magnetic fields are related to the strain tensor and lattice momentum of the models, and that their equation of motion, their trace of the Ampere equation, for instance, is related to a continuity equation for these. So this is a nice application of fractal models in 3 space-time dimensions.
Can I go back? Because I still don't understand how I can infer that these things are moving in planes, and because these are just static equations. So I'm confused as to how I can see the dynamics of where they move from these constraints.
No, I mean, if, for instance, just going
It
back.
sounds like I'm supposed to be able to see that, but I just can't. I can't connect the movement with these constraints.
Okay, it's just telling you, I mean, for instance, just looking at these relations, the scalar charge, talking about fractons. So if we have,
Just to clarify my problem, if I take a point charge, which satisfies Gauss's law, it just tells me that the field around it is a particular shape, but it doesn't tell me how the particle itself moves.
Yeah, no,
So
sure.
why can I see that these are restricted to planes and
Because of the fact that we have 2 derivatives. It's not a standard gas constraint. So this is the relation. So this is the dipole, right? The total dipole.
this tells me that this tells me something about the average of this quantity. It looks it's 0 as long as
or up to boundary terms. I mean,
as long as rho has some particular form, but that's telling me about the density of these objects.
Yeah, but I mean,
But it doesn't tell me how they move.
No, but it tells you that if you move one of these, you change the total dipole moment, right?
Yeah. So the dipole is intrinsically contained geometry.
Yeah.
Because if you move, if you have the dipole conservation, if one moves, one has to move as well in order to preserve the dipole.
Yeah.
Yes, but it doesn't tell me whether they can move at all.
No, then one has to show the full theory, right?
Sure. I mean, it's just
it is just a preliminary explanation. It's not the full Maxwell theory, but I'm just saying that there is in the quadrupole and dipole there is a geometry, the concept of distance between objects. It's absent in the standard Gauss law, right? So if something moves in one direction, another has to follow. Otherwise, it cannot move anymore, because otherwise you would break the dipole conservation.
I don't quite see
Yeah,
it.
but if you have
If I look at this equation here, it says the integral of xk rho. Well, rho is a scalar quantity, and if I average x over any direction, it's going to give me 0. It looks rotationally invariant. Maybe. It's telling it.
There is a sort of constraint, but you see the constraint in the dynamics actually, because the dipole conservation is very strong constraint, because it does not allow you to have 3 particles that move independently. They ought to conserve the dipole. So.
But it just tells me a property. This equation tells me, if I look at it, it tells me that that if I expand rho as some CJ x or some tensor coefficients times x. If I look at the linear one, it says that rho times that ci xi times some function of x. That coefficient ci has to be 0, but it doesn't tell me much more than that.
No, I mean this does not. This is not enough again.
It's not enough to tell me much other than properties of the distribution.
No, true. So it's about this. I agree that it's a static part. The dynamical part has to still have.
It's not telling you how the dipoles, for instance,
the rest of the dynamics.
Yeah.
So this was.
And it's a continuous statement, so it's very hard for me to connect it to a statement about the motion of individuals or pairs. It's a density statement. It's probably about the density.
Yeah.
The density can never have a term that, for instance, a linear dependence on x. There's some scalar function.
But the dipole per se cannot be written in terms of a single particle. the dipole has to be, you know, a relation between two particles in the system. So that's why.
It's telling me that the dipole moment of the thing is.
Yeah, yes, yeah, that is the thing. It has to be conserved. So what means that the dipole?
But it's a continuum statement. It's a continuum statement about the dipole moment of this system.
Yeah.
That there's no dipole moment in the density.
No, that. Yeah, but the dipole conservation, I mean, it's like, as I said, the charge conservation doesn't tell you anything about the dynamics of geometry.
No, it doesn't.
It's a Human internal system, but the dipole is a geometrical quantity. It's a distance between two objects.
There's no distance between two objects really here, because this is just a statement about the density.
Not much of the distance, but more of the direction of the dipole. I mean,
it's telling me that the scalar function rho cannot have a certain moments. I mean, it's presumably rho, presumably the integral of rho itself is a positive quantity. It's in density, and it's telling me this is a probability. I can think of this as a probability distribution. A probability distribution has certain moments that are absent. That's what that's telling me. And the dipole moment is the obvious one that's absent.
Would it help if you think of it as something that is on the lattice, so you don't have...
If you wrote a lattice version of it, you could tell me what that would imply more.
Yeah.
But this is not a lattice version, this is a continuum one.
but it's taken from lattice. Yeah, I mean, it's this is inferred from lattice model and taken into the continuum. I think this is based on the works of Bertolini. I think it's
Sure.
he takes from lattice models and then studied this on the continuum. And yeah.
Maybe it's better if you show the full equation.
Yeah.
I'm
Yeah.
much happier with full equation.
Yeah. So. Okay. Okay. So, this is the nice duality. One can apply this, and well, there are this duality also particle content, for which fractons can describe disclination, and dipole can describe dislocation for the reason of that disclination exactly behaves like a fracton. It cannot move unless producing a dipole. Like, in the sense, like the example on the lattice X cube model. This is just you can have a red dot here just moving just by switching the links here, and yeah. So this is an object made of 5 links, and the other are hexagonal lattice. Is an hexagonal lattice, and so by flipping the links, so we can have a 5 links object here, and 5 links object here, and 7 links here. So this behaves like dipole-like, or what's called a disclination, which can move linearly along what's called the Berger spectra by flipping some connections, while the fractons only can move only by producing this other object. So, well, this is just in curious relation, but
just some comments. This is 2 plus 1 dimension because the magnetic field is a vector. Because we showed before that in 3 plus 1 dimension, both the E and B are tensor. So this would be the dictionary works on the plane, let's say, not work exactly in 3 plus 1 dimension. Because you have the lattice that is always a vector, the momentum, and then you have referred to the B that is a vector. So that's why there is a dictionary, right? Because the B is a Bij in 3 plus 1 dimension, right?
yeah.
So that's why it's a very specular 2 plus 1 dimension.
Yeah, it is, because the duality comes from some sort of Faraday equation for fractons and a Newton law for elasticity, and they match in 3 dimensions.
Sure. Because 3D, that's why 3D is 2 plus 1. Then.
Yeah, it's always 2 plus 1, yes.
So I'm missing it.
But that's just a curiosity. I'm not
I mean, it's true that the epsilon tensor requires there's a spatial, a two-dimensional space. Is
Yeah.
that what you're referring to? You've got an epsilon ij.
Yeah.
The I exists
Yeah,
in
sure,
any
sure,
dimension.
sure, yeah.
Would you call it a magnetic vector? I don't know what that means. It has nothing to do with magnetic field.
Because it does some kind of Maxwell-like equation.
Yeah.
Yeah.
So the tensorial magnetic field in 3 plus 1 dimension becomes a vectorial again in 2 plus 1.
It's like in Maxwell theory, it is a vector and it
Yeah.
becomes a pseudo-scalar in 2 plus 1 dimensions.
It's similar to the idea that in Maxwell theory you don't have the magnetic field in 1 plus 1 dimension, right? You know, that you do something when you have a lower dimensional system.
So you're beginning somewhere different to what I see on this. I mean, I don't see that this has any relation to Maxwell fields yet. It's just
No,
that's just
this is a
like,
vector field that you're saying.
this behaves like a
Magnetic
magnetic
line.
field.
Unless you
and
could
this-
need some equations for this.
No, sure. There are also
The Maxwell field, if you're thinking of the B field as a true form or a form, and that has that's a closed form.
right.
If you're thinking of that, but I don't. This is just
No,
a
it's
vector
not.
object here.
This is, of course, for now, it's just a magnetic like. It's not the real magnet.
What makes it magnetic like?
all its equations of motion of the theory are Maxwell-like. So you can define, I'm
What
doing
does
some
that
of,
mean? You're saying that it is a two form, that it's a one, that B is a one form or a two form?
yeah.
Or the dual, B is.
There is a dual.
Normally
yeah.
you think
Yeah.
of the B field as the dual of a two form.
Yeah,
in three
it's
dimensions,
something like
which
a
gives it its
three-form,
vector
yeah.
index, but it's naturally two form.
Yeah, you can define it starting from a field strength and the contraction with an epsilon, so it's a dual of this object.
So you want to think of B as a dual of a two form.
Yeah. But
And
this,
And it's a closed two form.
uh,
There are no sources for it.
no, it's, you know.
So it's not Maxwell-like.
So, I will tell you, I'm gonna be there in a moment. I mean, indeed, I was just saying that there are some weaknesses in these models, which, well, mostly from the quantum field theory point of view, because many of those objects are made ad hoc just to implement all these gas constraints and limited mobility just to have fractons. All that A0 object is put there by hand because they want the Gauss constant, the theory is fully non-covariant, there is an inhomogeneous number of derivatives in the theory, and there is an issue concerning mass dimension in the symmetry, meaning that the gauge field has mass dimension 1, we have 2 derivatives in the symmetry, so it means that the gauge parameter has dimension as negative mass dimension, so this is a bit of an issue. This would be recovered in 6th dimension, which is quite recurrent in fractal models. So 6th dimension seems to be quite interesting, which we will see for some reason. So for this reason, I started working on a Maxwell theory for fractons from a quantum field theory and covariant approach based on the symmetry. So what I did was first promoting the fractonic symmetry into a covariant symmetry. So thinking like what one can do with Maxwell theory, so from the symmetry one can think of building the most general invariant action, and from there one can get the equations of motion, and then all the physics just comes out naturally from the symmetry. So the idea is the same. We want to start from the covariant symmetry and get the action and the equations of motion, and let's see if we really have fractals there. So here the symmetry, locality, power counting, and covariance are the only ingredients. And so, what happens is that by asking what's the most general invariant action of this symmetry, we get this first result. So we have that the space of invariant functional is dimension 2. We have 2 dimensionless parameters, G1 and G2, one of which can be reabsorbed by the definition of fields. But however, it is interesting that they are both dimensionless, which is first time, I think, that I've seen something like that. I'm thinking, for instance, another case is 3-dimensional, space-time dimensional, Maxwell-Simmons theory, but in that case, one of the two parameters is dimensional. So we have a mass. We can identify one of the two parameters as a mass. In this case, this does not happen. So what's the meaning of these two parameters? Still to understand that. Also, well, one can decide to make them however one wants, but I decided to organize these functions this way because one of the two terms is immediately recognizable as the linearized gravity term, which is this one. And this is the first result because it was always suspected of a relation between fractons and linearized gravity due to the fact that we are dealing with the rank 2 symmetric tensor field, but the relations were more subtle. However, here it is immediate. It comes directly from the symmetry because covariant fractonic symmetry is a particular case of the diffeomorphism symmetry, which means, well, which is also sometimes called longitudinal diffeomorphism. So you have linearized gravity along with fractons in this case, and this is a little bit of an issue too, because in a sense you don't have a way to separate linearized gravity from fractons. You cannot isolate fractons from a symmetry principle. So if you ask for, at least for my knowledge up to now, because if you ask for fractonic symmetry, you always come out with the linearized gravity term too. While on the contrary, you can isolate linearized gravity by asking the invariance under diffeomorphism symmetry. So, well, the first thing is, well, that's a curiosity. Well, one can study the gauge structure of a theory, looking for the degrees of freedom and propagators and gauge fixing. And, well, this theory is also peculiar from this point of view because, well, following the standard theoretical procedure, so by looking at the gauge parameter, which is scalar, one should build a gauge fixing term, which is a scalar gauge fixing term. However, looking at the left-hand side of this relation, we're dealing with the rank 2 symmetric tensor field, like linearized gravity, in which the gauge fixing procedure is vectorial. So which one is the right one? Which one works? And what's surprising is that they both work. And yeah, and also in the sense that both have the same counting of degrees of freedom, apart from the fact that clearly linearized gravity limit does not work in scalar 1. But the vectorial gauge fixing is preferable for the fact that the scalar 1 is only possible in the Landau gauge, so it's only for the psi term being equal to 0. This analysis also shows an additional pole to the propagators, which has a particular meaning. Indeed, we have here 5 degrees of freedom, and we will see that this is a traceless theory, which is interesting. And yeah, I'll show you later. So, what's next step? Thinking of a Maxwell theory is to build an invariant field strength, like the Maxwell field strength. So, by asking it for it to be depending on the derivative of the gauge field and being invariant under fractonic symmetry, we have this field strength, which is symmetric under the exchange of the first two indices, and this also has a sort of cyclicity property and a Bianchi-like identity. So this is surprising because from this field strength you can write both axes, the fractonic one and the linearized gravity one, both in terms of this field strength. And in particular, the fractonic one looks like a Maxwell term, so like net square term. Know this because in the literature, you always see that fractons are Maxwell-like models. And so from this idea, we indeed notice that we have an S squared function. So, oh, this is a curiosity, and yeah, the responsible of this remark is sitting here in this room, and yeah, at some point he was reading our paper, and he came up with this paper of Wu and Z in 1988. So there were no fractons at the moment. I was showing you first fracton was in 2005, and in this paper, the same field strength and same covariant symmetry appeared at the end of the paper and in a number equation. We still don't know how we could remember something like that, but still.
So
Yeah.
I remember reading this.
Yeah, I remember this paragraph.
For some reason, yeah, completely nothing to do with fractals, but yeah.
The older the better, little.
Oh yeah, sure, yes. Still remembering the final word, yeah, I mean. And it's remarkable also because after this, the second time this field strength appeared was something like 40 years later. So it's quite, yeah. So going back to more serious things, one can compute the equations of motion of the full action and the canonical momentum of the theory, which, for instance, in Maxwell theory is the electric field, and we get that for the whole theory, so also for linearized gravity, for instance, we have a Gauss-like constraint. So if we stick to the fact that this Gauss-like constraint gives an immobility constraint, it's true that we are dealing with a fractal model. Also, going back to the pole of the propagator, so we notice that the theory is a traceless theory, and it still have a Gauss-like constraint. So it seems that here we have a full fractonic theory, and here we could have a traceless fractonic theory. So the one that has the dipole being a two-dimensional particle. So now we switch off the linearized gravity term. So we put G2 equal to 0. We want to study the S squared term. We know quite a lot about linearized gravity, so we keep that term on. We study this. So what do we know? We know that in Maxwell theory, the components of the equation of motion and of the Bianchi identity gives the Maxwell equation. So we want to see what happens in our case by looking at the equations of motion and of the Bianchi identity, which we have written in terms of this field strip, so this one. So by doing this, what do we have? Well, the first equation of motion, the 0,0 component of the equations of motion, does not remind of any Maxwell equation. However, it has an interesting solution, which is this one.
Just remind me, how is that, is your F mu related to the connection?
That is H mu. So the A mu is the H mu in the nearest graph.
Yeah, but F mu is,
Well,
how is it related to some connection? I mean, like in GR?
in GR,
It must be some.
well, there is no, wait, no. There are different ways to understand that, but she's talking about basically something that looks like the theory for gravitational waves, right?
I see.
Right? So the gravitational wave you end up with, the wave equation for
Which are the-
H mu.
Your connection is the first derivative is a 3-index tensor. It's symmetric in 2 indices.
Yes.
Yeah, it's similar, but it's
So
not
it
the
cannot be a
same.
form, it's not a form. It cannot be a form.
This is not really a form either.
No, it's actually the graph is
So the Christoffel symbol is.
so in the Fritz-Pauli theory, in the linearized gravity, you end up with something that has a Bianchi identity,
Yeah.
but doesn't have really a form. And,
So is this the same? Is F mu the same as gamma mu?
No.
no.
it's similar, but
It's,
yeah, wait, I think, yeah,
okay, this is the
there is
expression,
a
okay.
two, no, this factor two makes it,
it's the
definitely.
two there that
Yeah.
you're clean.
Well, if you think of the Christoffel symbol, it's not invariant under the fractonic covariant.
Yeah,
symmetry.
yeah.
So that's maybe the quickest way to think of it. Indeed, there is something.
So she's taking a sub-group of the diffeomorphism.
Yes, I can see
It's
that.
not the, so it still cannot be invariant under linear diffeomorphism, but can be invariant under longitudinal diffeomorphism. It's a subclass of, sorry, a subset of diffeomorphism.
Yeah, the one
This
where
one, in gravity they're called longitudinal, that's very special kind of diffeomorphism.
Yeah,
So it's
well,
the Christoffel symbol with an additional term on it that's coming from some scaling. Is that what it is?
Christoffel symbol is scalar.
With a gauge scale of some way of gauging the scale or not the scaling.
Gauging the scaling.
It looks very close, but
It's quite similar.
there are different ways of playing with those connections, which okay, anyway.
yeah, there are some interesting things related to Christoffel. Maybe there is some interpretation of fractons and torsions stuff. So maybe.
Yeah, I think it's better.
Yes.
Have a full torsion full theory of gravity.
Yeah, no,
Yeah,
I mean,
that-
if you
that's
put in a
what-
torsion map as well,
Yeah,
it could be that
Yeah.
you've tied the torsion.
Yeah, that's
That's what I was-
one of the ending points for concerning the future. So yeah. I don't know what the answer is. So no, too much. Okay, I was there. So we have a particular solution from the equations of motion, and applying this to the definition of an electric field from the field strength, or looking at it as the canonical momentum, they coincide like in Maxwell. We have that this electric tensor field coincide exactly with the fractonic one in the literature. So this A0 come back, but for us it's coming from a solution of the equation of motion, while there it was imposed as a multiplier to implement the Gauss constraint. So here we have it naturally in the sense. And the definition of the magnetic field is simply the curl of this of the rank 2 gauge field. So by looking at the other equations of motion, the Bianchi density, and keeping in mind this solution, we find that all the equations of motion, all the equation matches exactly the Maxwell one as a higher rank extension, and they also coincide with those used in the literature that are typically or either imposed or coming from something that is imposed. So we have the Gauss constraint, the divergence of the magnetic field, a Faraday law, and an Ampere equation. They all match the fractonic equations in the literature. So the claim here is that fractal models are embedded in the covariant theory through this particular solution. We can do the same by looking at the action, and also that one, in terms of the electric and magnetic field, remains strikingly as a Maxwell theory. Also, computing the energy momentum tensor as a variation of the metric, we have the energy density of the theory, which matches one of the ingredients of fractal models, and it allows us to constrain the coefficient of the theory, because we want to have a positive definite energy density, and all these components are a I-rank extension of the Maxwell components, so thinking of the Poisson vector and of the stress tensor. Also, well, some differences from Maxwell theory. Well, we have a trace which is non-zero in 4 dimensions, so we have a favorite energy scale, However, it appears that in 6 space-time dimensions, we recover tracelessness. And that is the second time that 6 space-time dimension appears. So both here and in the issue concerning the mass dimension of the fields. So it appears that for some reason, which I don't know which are, 6 dimensions are favorable for fractals. Also, there is some kind of issue in the sense that the energy momentum tensor is not fully conserved, or better, its energy component, its zero component is conserved, so we have energy conservation, but it's not conserved in this spatial part, which may mean that we don't have translational invariance, which, well, it's understandable for a fracton, which is an immobile object.
There's no way of defining an improved energy momentum tensor that would be traceless.
So, meaning like,
So there are some extra.
you know,
Yes, we need
To force traceless. So in order to get traceless theory in 4 dimension, one should have some extra term.
yeah,
Because itself is not.
yeah, by itself it's
You have
not.
many options, is the problem.
Yeah.
The usual one is to add in, for scalars, you add a coupling of the curvature to the scalar squared. Here you could have an R mu nu, which is a nice symmetric tensor. You could add it to the field itself,
Yeah.
for instance.
Yeah.
Yeah, I mean, however, this is telling something, and yeah. Then we can also think of adding some kinds of matter coupling, so adding some source for the theory in the action. The equations of motion are modified like this, so the Gauss constant has its proper rho, which is identified as the divergence of the zero component of the current. And from the cyclicity property, we have the continuity equation that I wrote here, which is also another sign of dipole conservation. So, and it's typical of fractal models. So, keeping this result and the result concerning the energy momentum tensor, we can also compute the Lorentz force from the functional conservation of the energy momentum tensor. And this is interesting and important for 2 reasons. The first is that in the literature, it's one of the other things that's both come out from nothing in a sense. Like Fresco in his paper writes, by intuition, the Lorentz force for fractons is this. That's cool because it matches exactly ours, but it's not exactly a formal way, and we get the same, exactly the same, starting from the symmetry principle of the QFT. And also, it's important because we have a confirmation that we're talking about a fractonic theory, in the sense that if we see this A0 as a dipole, well, what's the object that can feel force? It's not a fracton, because it's an immobile object. It cannot move, it can feel force. But it can be a dipole, which is free to move. And indeed, this is what we have. This is the dipole, and that's the dipole current. That's identified here. So these are all integrated quantities. So, yeah. We have a well-defined Gaussian theory for fractons that comes out from first principle of QFT and matches the results with the literature, so we are confident that this is a good theory, and one can apply all the QFT tools to study that. And, well, in my past years, I've been interested in studying boundary effects on models and studying the physics of boundary on some QFTs, both topological and non-topological. So the next step, which will be quite shorter, would be to study the boundary theory of this fractal model. So just a little bit of introduction. So why boundaries? Usually people would say, well, let's put boundaries at infinity. These are trivial effects. We are not interested. But however, there are some cases in which boundaries are important indeed. First,
before you do that,
yeah.
You put in some curves and things like that. You didn't discuss how you would couple it to any other matter. This is a universe in its own right, except for gravity. You coupled it to gravity. You decided you could couple it to gravity by minimal coupling.
Yeah.
But was it not possible to couple it to something else, some other?
I mean, what do you mean coupling?
An interaction.
Yeah, we have no interaction of two.
You have no interaction at all,
No.
except you did put in an interaction with gravity.
But it's not really an interaction. I mean, it's quadratic theory.
It's minimal coupling. You minimally coupled it to gravity.
Okay.
So that's where you got your stress energies.
Okay.
But did you could try coupling it to some other some other fields.
Yeah.
Sure,
Other-
you might
yeah.
couple it to
There are some,
temperature field or something.
Yeah,
Scalar fields,
Yeah.
which represents the temperature.
Yeah, there are some models which couple some fractonic matter fields. So yeah.
Field has been done.
Yeah. Scalar
Scalar
fields.
field has been done.
Yeah.
The problem is that it's not.
I mean, does it introduce it? Typically, if I do that and I quantize it, I do some statistical fluctuations on it, it will induce additional interactions, which will force you to generalize the model and go away from linearity.
Oh yeah, sure.
Has that been looked at?
Not yet, but we are thinking of coupling this fractal model with some kind of
But naturally, the easiest one is to try coupling to some scalar.
Yeah, sure.
Just not true. Another bigger question is how to couple to fermionic matter. That is almost nobody knows how to do this. For sure, I can tell you this, that we are trying to think but today it seems that because you cannot put this tensor inside any direct operator. So the problem is that how it's a highly material. Even at the end, it is sort of an abelian-like theory.
It is
Yeah, definitely.
But still, the coupling with fermions is something non-trivial.
Yeah, also with scalar.
Yeah, with scalar again,
Yes.
they ended up with the scalar with the complicated scalar
Yeah.
theory.
Some
I
covariant
mean,
derivative, which is
yes.
quite different.
For instance, you can have a Goldstone-like mode. You can have something like that. In the sense that
some additional symmetry, or you could just try to do a single scalar.
Yeah.
To move with us.
Okay. Yes. No. This is true. Yeah. No. This has been done more or less for scalars. But again, there are a lot of open questions about fermionic matter, as you say, with the full interacting theory. How it looks like. This is an open question.
You might be able to couple it with field strength to the family.
The field strength again. Yeah, sure. No,
No,
well,
no,
no minimal coupling. No minimal. Yeah, no minimal coupling. Yeah, I agree. It's like a Pauli,
Exactly.
Yes, so this is the only one that. But then you have to combine also. You have to saturate the indices with the gamma matrices, and there are 3 gamma matrices now, not 2. I mean, in the sandwich between psi bar and psi, you have to one has to something like.
That could be an option of a gamma matrix of a derivative.
Oh, so you have in mind higher derivatives. Yes, that's no. The question is if one wants to keep or not the Lorentz symmetry. This is the question because
this is just saturating in the schedule, for instance,
yeah. Ah, yes, P3 is much more.
Yes.
It would be more easy. No, I agree. Yeah, in principle, but they could exist also fermionic fractals in principle. One could build everything in terms of linearized supergeometries and linear geometry. Yeah, this is another open point. Very good point.
Okay, that's the quick next step. There are many examples of the relevance of studying boundary in QFTs. Well, one of the most notable maybe is concerning topological quantum theory, which are interesting theories, but on their own, not much on the physical point of view, meaning that they have no momentum tensor and no momentum tensor. However, when one adds a boundary, then you can find on this boundary local observable and then identify some kind of physics on them. So, for instance, for a Schwarz type topological theory, one can have edge states of fractional quantum effects on the boundary of the three-dimensional transcendental theory, or edge states of topological displaces for three-dimensional or four-dimensional data.
So was it obvious the theory was unitary? You just told us about the classical theory, but wasn't obvious to me that you had a unitary theory here for the quantum evolution.
So the question is your fracton theory unitary?
Yeah, well, it just have a ground state. Is it the energy bounded from below? There are lots of quantum questions that.
Yeah, I mean, there are lots of things to do, but yeah, surely it's bounded by below for the energy density. That's, you can see.
At the quantum level. This is all classical. So.
Yeah, sure. No, we didn't check this, yeah. But, yeah. And.
Calculator looks weird for it, so I'm not sure what will be what's so well defined. But I don't know.
So, there are some things to check still. I mean, it's new, so. Well, that's another example of field theory with boundaries. Yeah, ADS-CFT, which we were discussing with some guys. And yeah, that's another example which was born in context of string theory, and well, it's five-dimensional theory, for instance, of general relativity with an ADS metric and a conformal field theory boundary. And now this is having quite interesting results in the context of condensed matter, and people are doing experiments with that. In particular in the context of superconductivity and strange matters. So that's just another example. From the QFT side, the first work concerning QFT with boundary was done by Semantic concerning the cosmic effect, who was thinking about what's a boundary in QFT and what were the formal consequences of the boundary, thinking of a double-sided boundary. So, the theory both existed in one side and on the other, and that was related to the property of separability of the propagators, meaning that propagators of the theory of points lying on opposite sides of the boundary had to be zero.
I mean, this is the paper where he set up the Schrödinger equation for quantum field theory.
Yeah.
So but don't think that those properties are generic. There's a lot more freedom there.
Yeah, I mean, it's just how to impose a boundary in the QFT. I mean.
Yeah, but you don't need the second side.
Indeed, I know. Indeed, it's what we do. We don't
But you
consider
do need
second
this notion of evolution in Swanson's case. Because you're
Yeah.
evolving something forward in time.
Yeah. That was just another example. We take something from the ideas of semantics, but not that part. So what we do, on the contrary, is considering a one-sided boundary. So theta-like term, and we want to keep. So I'm making an example concerning the Chern-Simons theory. I want to apply this technique to the fractal model I found before, but well, just to be quicker with the computation, it's easier to show on a model like Chern-Simons, which is easier in the sense that it has shorter equations. And so that's what we do. We want to stick to the idea that we don't want to impose anything by hand. So, but we still have to consider boundary condition and to keep them as general as possible, as much general as possible, we consider this boundary term, which is the most general boundary term possible, with a generic matrix. And this was first done by Szymanczyk in the previous paper. And so this gives, from a variational principle, this gives the most general boundary condition, not being Dirichlet-like. So then, from adding a boundary, one break gauge symmetry, for instance, and this gives a breaking in the word identity from the right-hand side, and this will give us the opportunity to find the local degrees of freedom of the boundary to be scalar fields as the most general solution to this on-shell equation, meaning that at j equals 0. So we find in the Chern-Simons theory, one has that the boundary degrees of freedom are scalar field, and in particular they are chiral scalar fields. And one identifies also by taking functional derivative of that word identity. One also finds an algebraic structure which is a Kac-Moody-like algebra, and this can be related to the Kac-Moody algebra of the edge states of the quantum Hall fact, and this allows to relate the coupling constant of the Chern-Simons theorem with the fitting factor of the quantum Hall fact. So from these ingredients, one can find the two-dimensional theory, two-dimensional action being invariant on the transformation which keeps invariant this definition, which is simply shift symmetry of the scalar field. And by looking at the Kac-Moody algebra as some kind of canonical commutation relation. So by looking at this, we have that the two-dimensional theory is the Luttinger model for the theory. So we're talking about chiral moving about. The final step is to match the bulk theory and these parameters, which are just the A, which was appearing in the boundary term, and the coupling constant, which is related to nu, with the coefficients of the equations of function. So this just gives an additional relation for the two sides to match. So this is the general idea, and I want to do something like that for fractals. But why? There are some physical motivations for this, and yeah, the first one is that fractals are some kind of Maxwell-like theory, higher rank Maxwell theory, as I was showing you at the beginning, and Maxwell on boundary have describes edge states of topological oscillators, and it appears that fractal models are related to fractal models. Edge states of fractal models are related to edge states of some kind of higher order topological oscillators. Like, for instance, in this paper, they try and do this kind of matching. They find some relations. So these are the motivation for studying the boundary of fractals, and in particular the covariant theory we found before, so we can apply the QFT tools. And just doing all the computation I showed you in the Chern-Simons case, we land on this three-dimensional, 2 plus 1 dimensional theory, which is a Maxwell-Chern-Simons-like theory, meaning that this is Maxwell-like and this is Chern-Simons-like, but they are written in terms of rank 2 traceless symmetric tensor. So again, it's a higher rank theory. And from these, the equations of motion are Maxwell-like, one for each field. You have the Gauss and the Fairlight equation, where the Chern-Simons-like term is related, is playing the role of matter, of fractonic matter, so a rho here and the JMM here. But again, it's a traceless theory, and the electric field is traceless, so it appears that on the boundary there is a traceless fractal theory. So the one I mentioned at the beginning, so with the constrained dipole movement. Concerning the physics, we find that there is an algebra which is not exactly a algebra, but some sort of generalization with two derivatives.
So in this case, in the fractal case, you still get a 2 index.
Yeah.
Rather, it doesn't go down to a 1 index.
No, exactly. No. But it's from a traceful field, you get a traceless one.
Your example earlier was for abelian Chern-Simons.
Yeah, that was for abelian.
What was the secret that brought it down to a scalar?
That was simply the solution and the counting of 3 indices. There was a curl of A,
Yes.
and the most general solution is just the.
Right, but it was the divergence here.
Yeah.
So, and why doesn't one of the indices disappear in?
Because that's, I mean, you have.
In your fractal theory.
Yeah. I mean, you have.
I think the derivative is the point, right? I mean, if you take the Maxwell in 3 dimensions, you do the semantic, you end up with the Maxwell also.
Yeah, it's again, also
So
Maxwell is a vector vector.
Exactly, the vector also.
Yeah.
Is that is a Chern-Simons, that is the first derivative that gives rise to a scalar on the boundary.
It's the first derivative.
Yeah, but that is the difference.
I see. Yes.
So,
Okay. Yeah. No,
Yeah, for Maxwell we have something like the divergence of A being equal to 0, so you have the curl and so again a vector. And for fractals it's something similar, it's the divergence of the rank 2 tensor, or the double divergence, I don't remember. And the most general solution gives you another rank 2 symmetric tensor.
You could have looked for a first order derivative
No.
theory for the fractal. Could you?
yeah,
Maybe I didn't.
and you have also this new paper about Chern-Simons, like
Yeah, so I missed the question.
to have a first order fractal.
Oh, yeah, sure. Something like, a theory just like this. Yeah. That's what I'm doing at the moment. Yeah. We're going to finish it in a couple of weeks. And so here again we have some kind of traceless fractal theory on that. So I was saying this already. And here we have indeed a relation with higher order topological insulators through this generalized Kac-Moody algebra, which is of the same kind that was found in this paper. Indeed, when they were searching for these estates. Also, since we are dealing with the 2 plus 1 theory, there is that fractal elasticity duality, and these equations are similar to the Ampere equation I was mentioning at the beginning, so it seems that it could be used, that does, and also in this paper, they're starting from a Chern-Simons torsional theory. They end up on the request of area preserved diffeomorphism. They end up on a theory like this, on the Chern-Simons-like theory, no covariant theory. So,
You're saying this Gromov.
Yeah.
So what was their theory? Just the area preserving diffeomorphisms was really interesting. So can you repeat that comment?
So this guy starts from a torsional transensemble theory, and under the request of area preserving diffeomorphism, and maybe there is another request.
So this torsional transensembles is like E wedge T. So E is the drive ion and the T is the torsion.
Okay.
It looks like a transensemble, right? Because it's a E wedge D.
Yeah.
And then they impose also just the area preserving
Okay, that's
diffeomorphism. It's the only constraint that impose. And then it gets back one of these transensembles like it gets that term there.
Something like that. It's non-covariant, maybe.
In a non-covariant.
Yeah,
Everything
but
is.
So what is the two-index tensor in that setting?
The two index, so is a torsion is no sorry.
Comes from the real line.
Yes.
Well, let me think. Well, he imposed this diffeomorphism, no? The unimodular gravity, basically, so he put the determinant of the linearized drive ion as the equal one. And then he solved this equation. By solving this equation, he gets an emergent.
Is the A there in his one coming from the torsion field, from the connection?
Well, no, actually, omega is not
It's
important.
anti-symmetric, and that's it.
No, it's not important. Everything comes from the theta, from the drive ion. So you can also put omega not zero. It's not important. Is that it's really E wedge DE.
But the torsion term is an anti-symmetric object.
Yeah, it's at 4.
So that means that little a tilde CD must be anti-symmetric in that case.
No, there is a problem. No, there is a problem because E so is completely metric independent. So it's a topological metric independent. Now this theory is not really topological. So there is an inner product there.
It's a BF theory.
There is you see the inner product, so there is a summation on the D.
Yeah, there is the fraction.
So it's not really a topology. It's a Chern-Simons-like in the sense that it's not really Chern-Simons.
But in Gromov got it about.
He got imposing a constraint. So the constraint is geometrical. It's the area preserving.
But his two-index object was anti-symmetric, presumably.
Well, no. At the end, no. You end up with something that is symmetric.
Yeah.
You end up because at the end, again, the drive ion is related to a linearized graph. I mean, you can.
That's right. But you have the drive ion, but you also have a torsion connection. You've got the torsion field itself,
right,
which is anti-symmetric.
Yeah. But we have to impose. Okay, so the drive ion is a space-time index, a gauge index.
Yes.
Then you can maybe, if I remember correctly, how is it? I think that one of these two indices there is gauge. And then, but then you go to second order. If you go to second order, all the indices are space-time.
Okay, so they're not they're indices of different types.
Yeah, there are different kinds of yeah.
All right. Okay. You will get that, yeah. So there's not necessarily symmetry.
Yeah, well, this pretty much end it. I mean, there is also this self-dual massive gravity, which shows these same transensemble terms. So this is another relation from this theory. But yeah, okay, that was so. Just going to the conclusion and not because there are so much to discuss yet. Well, from the beginning, we managed to build a covariant Maxwell-like theory for fractals, just starting from the symmetry, and this confirmed from a first principle QFT point of view the results that are typically put by hand or transferred in the literature. So we have the magnetic and electric tensor field, the zero field motivated, the Maxwell equation, the energy density, continuity equation, and Lorentz force and dipole. We also saw the equation of the peculiar gauge structure of the theory, the energy momentum tensor, and the immediate relation with linearized gravity. Also, on the boundary, we get the three-dimensional traceless theory for fractons, a generalized Kac-Moody algebra, shows possible relations with higher order topological insulators, and all these connections with self-dual or torsional gravity, and possibly with elasticity. So, concerning the future, there are many points to add after all these discussions, but yeah, these were something I was thinking at the beginning. So the 3-dimensional, 2 plus 1 dimensional fractal models are currently under study, at least also from the elasticity side. Well, thinking of Maxwell theory, one can think of a non-abelian extension of models, or Young's-like theory. One can study the traceless model also in 4 space-time dimensions, and thinking about a matter complex with scalar or fermions or whatever, something like a fractal 2D. Thinking about fermionic fractals, so again, what we were discussing before, a relation between fractals and torsion, and all the other connection models with linearized gravity and gravity itself. And yeah, here I stop. So, if you have many other questions, do you mind?
So everything you said was basically the fractals.
Yeah.
Can you do the same for lineons, planons?
I mean, this theory may contain planons or lineons, because, for instance, one of the constraints is a vectorial constraint, so this means that you have both fractals and lineons, or also the boundary theory, which is the traceless one. This means that you have both the fractals and the additional constant on the dipole, which lowers the mobility of the dipole. So, in a sense, you also have those kind of particles. Yeah.
I've only really seen fractons where lattice connections do with slope normalization that you mentioned in one of the earlier slides. And I was just wondering if that kind of slow thermalization behavior that comes with fractons in lattice forms, if that makes sense in this kind of setting, or if it doesn't translate at all.
I don't know.
Yeah, because the fractons are important because they don't normalize.
Yeah.
That's why there are connection with quantum scars and things. No, I think one of the main points by Erika was at the beginning that she distinguished these gapped fractons to gapless fractons. Okay, so what you're talking about on this lattice model is our gapped model, and they are not described by this H theory fracton that are all gapless. So
maybe you can find a massive model
yeah,
for fractals.
But let's say that, of course, if one can build a gauge theory for the other one with the non-thermalized, maybe that makes complete sense to ask, the thermalization of the lattice can be reflected in the non-thermalization on the level of field theory. But this can be done, I think, at finite temperature of field theory. Yeah. So, so I think this is the main difference with those models.
Well, can we see the action again, just for that? Because I'm curious about the propagator
With
and the unit 4.
this one is okay, or
No,
okay?
see a bit more in detail. So there.
Just like this.
Yeah, here it is.
Yes, okay, yeah, these are the two. I'm wondering if there is some way of adding in some mass term to this.
Okay, that's an interesting question. Well, without breaking the symmetry in 4 dimension, it's not possible. One can do this in 3 dimension. By adding that Chern-Simons theorem and keeping the dimension of the field being 1/2, then you have Maxwell, Chern-Simons-like theory, both with linearized gravity and this fractonic term and the transimulus-like term, that transimulus-like term then have a mass term, and so there you can have a mass. But that's three dimensions, three space-time dimensions.
Here, I think also you can use a Stackelberg field or a Goldstone-like, right?
Yeah,
These
that's
are
what I was thinking, that
yeah.
there was something like that. With so
So,
many
by
derivatives.
breaking you one, right?
You
So
can
many
also do
derivatives
something like
floating around.
Fritz-Pauli mass terms if you want.
It's scalar field.
Yeah,
Unified scalar field.
yeah, scalar, like, yeah, exactly, because it's double derivative of the scalar minus the fracton field squared, and that still gives you
This
value.
recoupling to a scalar.
That is a real scalar.
Yeah.
That
So
you mentioned.
something
Yeah.
Higgs that.
No, exactly. No, this makes complete sense. This can, or she said also that because this has a lot to do with linearized gravity, there is the Fritz-Pauli master.
Yes.
Although that one should break.
Yeah, that's break the symmetry.
Yes, but the question is, I don't remember because the Fritz-Pauli master breaks
Which is the fifth polymaster?
the fifth.
Can you write it down?
It's
I think it's something like h squared
Yeah,
minus
h
h mu or something like
this
that.
is,
Yes, okay.
I don't remember. So this breaks the linearized diffeomorphism, or
Yeah.
maybe keep the longitudinal, break everything. I
Yeah,
don't remember.
yeah, also.
So H is the trace, is this?
Yeah,
That's
that's.
So the trace in this case.
Yeah, it breaks both.
That's the problem. That's all. Yeah, this maybe it's not.
You can do this in linearized gravity, but it breaks the symmetry.
Yeah, I think it also is much more interesting.
Yeah, but in the three-dimensional case, she's
Oh, yeah.
this topological mass term, which is probably fun.
Yeah.
Is it object key?
It was a Jakiv
Yeah,
template
Templeton
on
and-
this.
yeah.
That probably makes more sense for the physical categories.
Yeah, but actually in this paper by Shao and Seibert, they discuss this, also the field theory for the Gaussian model. They end up with a scalar theory. It's a massive scalar theory.
Okay.
So with high derivative. It's a little bit similar to what Eric has showed the chiral boson, but it's only that it contains higher derivative.
Yeah, it's for
And they are not, these are all, so Seibert does not consider covariance. It's completely break Lorentz symmetry. So all the fractons break usually Lorentz.
Yeah.
I think this is the difference. Maybe Eric, you should emphasize that your approach is more Lorentz invariant.
Yeah,
Because all the rest is all these models completely don't care about Lorentz symmetry. So
Yes. But just to, I also still wanted to look at it from another minute, because I wanted to look at the linearity.
at the
It's not
action.
obvious that, yeah.
Yeah.
It's not obvious that it doesn't have negative norm states that would be problematic. Because you've got all this.
Yeah, this level is tricky.
Yeah.
I'm feeling like
Is the cage in there? It's not too, relax for you if you don't, until you apply the constraints, you have negative norm states as, the Klein spaces that you're taking.
okay, I know other people. Actually, also the speaker next week maybe is going to talk about this. I don't want to spoil it. There is this this idea that some fractals, not all of them, are related to Carolian gravity. The Carolian is the limit of gravity when C goes to infinity. And they are working a lot on this question about if Carolian is unitarity or not.
Yes.
So maybe you can think that also some fractals, not all this, but several fractals are related to Carolian, with this Carolian limit. So C that goes to infinity is also well-put limit. But it's related more to this, but again, you break Lorentz symmetry again, it's about.
Lorentz symmetry is separate from unitarity.
No, I know. I'm just saying that these are, are two different questions if you want to study unitarity in this context that she presented, or in this other Carolian limit, which is more, in line with these non-covariant models. But I think as long as I have still literature around about Carolian on this model, and also fermionic Carolian nowadays, they look all of unitarity. I mean, unitarity is preserved there.
Just what would the Hamiltonian be here?
So we have the Hamiltonian for this fractonic part.
Yeah, it is.
Yeah, it's E squared plus B squared.
Yeah, it's just like in the max.
Oh,
It is the sum. Yeah.
Yeah, that's it.
Yeah, and what is E?
E is the electric field.
But in terms of A,
It's
how do all the zeros,
yeah.
how do all the time derivatives disappear in the Legendre transform? You wrote an action which had lots of time derivatives scattered all over the place, the A naughts and I's and A naughts even. And you have all those terms are, I mean, it's not clear to me that the potential doesn't, that there aren't time derivatives floating on, that it's just E squared plus B squared when I did the Legendre transform there. You've done it, is what you're saying.
Yeah, I mean,
You take that action,
yeah.
you do the Legendre transform to go to the
No,
Hamiltonian.
No. I mean, we just compute the energy momentum tensor and the 0-0 component, which is the energy density. That's it. That's what.
That's not obviously the
Yeah.
Hamiltonian, the same as the
Yeah.
Hamiltonian from this action. Though.
Yeah, no, we
Not to me.
Yeah.
It would normally be,
But-
but you've got a very different theory, so I would need to check it.
I'm thinking. I mean,
If you go to your action,
I would say that yeah, everything works. Everything is compatible with the literature, and I think that in the literature everything is fine. So I would say that the Hamiltonian is exactly like E squared plus B squared.
if I read it, it was in the previous page or something.
This?
What was this one with all these A's?
Sorry, what?
Go back to the
One more maybe?
The action.
Yeah, this.
Okay. Here it is.
There. Now I should take the Legendre transform of this to go and figure out what the Hamiltonian is, just by the usual one.
Yeah, it's
It doesn't make it obvious to me that
No,
we get something.
I think you have a pi, no? The momentum pi ij, no? You wrote the pi.
Yeah.
I-
Well, it's
because it's from that
written
that you get.
Yeah. It's like in linearized gravity.
Yeah, it's like linearized gravity. I'm thinking mostly linearized gravity, but there's a ton of linearized gravity.
Would you need to impose all of the constraints to get something sensible in linearized gravity?
Well, in linearized gravity.
You need to go transverse traceless.
Yeah.
You're not going transverse traceless, you're keeping a lot of degrees of freedom, which would now be gauge.
Yeah, I mean, well, in the end, it's gauge there too. But, yeah.
I'm concerned that what happens to the but you've got the trace map we can throw away, that's
Yeah.
subscalar, you can deal with separately. The transverse modes are the longitudinal modes of this. Why are they behaving correctly from a Hamiltonian point of view? They're not present in the Maxwell case. The Gauss-Lock constraint forces a sufficient degree.
I think also the diffs that reduced to this simplified version that is much too apart. There should be a
That's a much smaller constraint than
Yeah.
transverse traceless.
No,
You only do transverse traceless.
No, otherwise you get like additional weight.
Yeah.
No.
But in the end, you have the same. You can fix the gauge also with.
But it doesn't look strong enough. You've just got this lambda as one gauge.
Yeah, but you can do a vectorial gauge fixing.
Sorry?
You can do a vectorial gauge fixing, like in linearized gravity. You don't have you don't change the degrees of freedom of the theory.
How many degrees of freedom are there in the theory? There were 5.
Yeah.
Gravity has 2 degrees of freedom.
Okay. Yeah. This means yeah. Because
So
yeah, we're saying the constraint you have from
the
the
3 degrees of freedom that I'm concerned about.
Okay, no, this is the counting that one does also in linearized gravity, just looking at the equations of motion.
But gravity has, in a Hamiltonian formulation, you can see that you have two dynamical degrees of freedom.
Yeah, but that's the same in the end.
There are
Yeah.
only two dynamical degrees of freedom.
Yeah.
That did not seem to be the case. And you've only one, well, I completely misunderstood if that's the case.
Yeah. Yeah, what we mean here with degrees of freedom is just the constant that you get from the equations of motion. So
Yes.
here you have the same for both linearized gravity and fractals. So they're both equal in this sense. They both have 6 or 5 degrees of freedom. Looking just at the equations of motion. So the constant you have.
That's very different.
Yeah, that's in quantum field theory. The definition of degrees of freedom is sometimes.
There's only two. Gravity only has 2 degrees. Of
Yeah,
freedom.
yeah.
I think maybe probably this is not compatible with the gravitational waves, right? This gauge fixing.
Well, the Victorian one is, yeah.
No, I'm
Yeah, this, yes.
right, but you don't get gravitational waves from this theory at the end of the day. So if you want to do all the calculation and
Well,
if
no.
you don't have traceless transverse condition, right?
No,
Yeah.
for the whole theory, no, you don't.
It just means that it's that what you're doing here with this is a partial gauge fixing, which is fine for some purposes.
No, I mean it's not part of gauge fixing. I mean from
If you
the
did complete gauge fixing, you would have.
gauge fixing is but in this sense, I mean gauge fixing is 4 constraints, right? It's
Sorry?
just gauge fixing is a constant of it's 4 constraints vectorial gauge
I think
fixing.
the difference is that you have this subset of diffeomorphism, and now you do the gauge fixing of this subset of diffeomorphism, not on the full. So one part of the diffeomorphism is gone, the transverse part, no, because you kill. So you have only this. So these gauge choices are compatible with this particular subset of the diffeomorphism that you can call longitudinal or fractonic. So I think it's not possible from just this theory to get all the standard gravitational wave. You need also the rest of the diffeomorphism that are gone.
Well, if you switch
Right.
G1 equal to 0.
Yeah, but then exactly. No, if you switch only to linearized gravity, the other diffeomorphisms are back.
Yeah.
And then you can do another the standard.
Yeah,
gauge
sure.
fixing. And then you
No,
end
that's
up
the
with
standard
only
gauge fixing still. I mean,
with
this is the
3
same
over 1.
technique.
Yeah.
If you apply this same technique
Mm.
to the linearized gravity theory,
Okay,
which has
I
been
know.
done, and apply this, you have these same counting.
6.
Then the rest, the remaining, the 2 degrees of freedom you're talking about, you get after studying the equations of motion. That's something that comes after. But just looking at, I'm saying just looking at these, the equations of motion you have here, you have this counting. Then it's another step to get to that counting. It's the traceless part that you're talking about. I mean, the transverse part comes from the gauge fixing. The traceless is looking at.
Traceless is trivial. That's
Yeah.
that's 1 degree freedom. You can throw that degree freedom away without any problem. I'm not concerned about that one. The transverse forces the gravitational one down to 2 degrees of freedom.
Yeah.
But it's not. This is just partial gauge fixing. Is what you're doing here.
Yeah, maybe. Yeah, it's a different.
Which is what's often done with ghosts.
Yeah,
It's like,
yeah,
okay,
that's
but that is
that's
not a real gauge fixing. That's trying to cancel some.
yeah. Okay, the redundant degrees of
freedom.
freedom. Yes, that's what I mean with gauge fixing.
That's not.
So
That's
okay,
really. That's not the same.
okay, then
In
okay.
a Hamiltonian formulation, you really have to bring it down to its physical degree
Yeah,
of freedom.
okay.
Otherwise, you have
Yeah, sure.
states in there which.
Non-physical states and that.
create
Yeah.
havoc
Okay.
with-
Yeah,
This is-
the first constraint.
Yeah.
Exactly. You're talking about
Yes,
One, I
it's
think,
really
no,
constraint analysis.
I think it's never done in these papers.
No, yeah.
Hamiltonian analysis.
Yeah.
That's why. No. I agree.
Yeah, okay.
Right. So
That's okay.
Yeah.
Then that's
there could
part
be
of
some
it.
serious
Yeah.
problems there, you see, because
Yeah, yeah,
of, of your analogy with gravity and having those longitudinal degrees of freedom
Yeah,
can
no,
create
okay.
havoc.
Yeah, this still we have.
For the covariant formulation, it doesn't matter that it's matter setting. They're just spatial things that are doing one thing.
Yeah.
To try and make it covariant
Yeah, that will.
is what I would be worried
There are
about.
some other things too. Still much work.
Sure.
And that's a good thing. So
Another question.
there's still that somehow.
Clearly a lot of work to be done here, yes.
Yeah, so
Early days.
she's the right person to
Sure.
to do all this calculation, right?
Yeah.